Welcome to this section of the course where we will be covering integration. We will be covering integrating standard functions, integrating linear functions that are within another function, integrating trigonometric identities and trigonometric functions. We're going to use the reverse chain rule. We will use substitution. We will integrate by parts. We will learn how to use partial fractions in integrations and integrals. We will find area under the curve, and we will also integrate parametric equations. We will approximate area under the curve with trapezium rule. We will solve and model with differential equations. And finally, we will integrate as the limit of sum. That is, some of you who are familiar with that. So, all of this, the preliminary knowledge required is chapters that involve differentiation and parametric equations, and and of course, knowledge of trigonometric identities is essential here. So make sure you understand the year 12 AS level maths before you take this part of the course. As I as I always say, make sure you also have a go at the preliminary prior knowledge questions before you start any chapter, and you review other chapters that are essential to it. If you understand differentiation very well, you should be able to understand this part of the course rather easily. Okay, so the very first chapter of this course is about integrating standard functions. So that means that if you know the reverse power rule, you you will be familiar with this very first equation. So that was used in AS level and is nothing new about that. We differentiated exponential functions and found that they represent a scale factor of themselves. So here exponentiation of x when integrated will give you e to the power of x plus some constant. We found the derivative of logarithm of x is 1 over x, and there are other scale factors of that. So when you integrate 1 over x, you are simply to choose the answer to be log x plus some constant c. We found the derivative of sine to be cos. So when you integrate cos, you should get sine. We found the derivative of cos to be minus sine. So we flip the negative sign here, and whenever we integrate sine, we will get a negative cos plus some constant c. And if you remember carefully, we differentiated tan, and we found the derivative of tan to be sec square. That's 1 over cos square. Therefore, when you integrate sec square, you should get tan, and you take that for granted from now. We found the derivative of cosec to be negative cosec times by cot. So when we have negative, well, when we have integral of cosec times cot with respect to x, we are going to put the negative sign in front of the answer, which is cosec, or rather the derivative. When we differentiated cot, we ended up with cosec, negative cosec. So when we integrate cosec square, we are going to get the negative of cot. And when we differentiated sec, we ended up with sec times tan. Therefore, every time you see sec times tan under the integral, you're gonna get the answer of sec x plus some constant c. So let's look at some questions here. Well, again, one more time. If you integrate a derivative, you will get the original function back. Should remember that from previous year as well. Here, if we integrate cos, we are simply going to get, or rather, if you integrate cos, yes, you will get sine. Okay, so here we are told that function is logarithm of x, and we know that the derivative of that is 1 over x. So if we had to integrate 1 over x, which is the derivative, we will get log of x, and we will add a plus c to the end of that. Because this is an indefinite integral. How do I know it's indefinite? Because we haven't been told about any values of the region over which we are integrating. So because here is nothing given to us, we need to put this plus c at the end of the integral. We make sure the values for logarithm are positive by taking their absolute value there. And in this example, we were told to integrate 1 over x. Now, there is a definite region of x values that are negative. So we are going to actually have to take the absolute value when we put the logarithm. So we cannot substitute negative values into logarithm because that just doesn't work. If you consider the shape of the graph of logarithm, it's actually symmetrical. So as I said, the negative values don't work very well, don't work at all. So actually, the logarithm, or rather the reciprocal function, 1 over x, is symmetrical around the origin. So this region here that I'm shading in red has the same area as this region that I'm shading in red here. So because of the symmetricality of the graph of 1 over x, we we can take the fact that these two areas are equal to each other and take values around and actually use logarithm of 3 and take away the logarithm of 2 from it. Okay, so you do have to switch the 2 around here. So you do need to have logarithm of 3 subtracting logarithm of 2, because logarithm of 3 is larger than the logarithm of 2. Or take the absolute sign of the final answer. Okay, so you will find these derivatives in your formula booklet, and they should be a very good clue when to use the integrals. So you're not specifically and explicitly told the integral of sec square is tan, but looking at the derivatives, you can have a good guess that the integral of sec square will be tan. Now we will discuss those how to adjust those constants and multipliers at the front in following videos. Let's look at the next example here. We are asked to calculate the integral of 2 cos x plus 3 over x minus x to the power of a half. So we can rewrite these powers in a little bit neater fashion so that we can see what's going on. We can factorize the 3 out of that middle term there. And when we have plus and minus signs between these terms, we can treat them separately as if there are 3 different integrals there. We know that a constant 2 in front of a cos function will simply mean that we can factor 2 out of that integral and integrate cos of x there, because the constant constant does not change uh, the function. It's outside of the function. It's multiplied. So we know that the derivative of sine was cos, and now that we are integrating cos, we will get sine back. So the first term will give us 2 sine x. Next term will give us 3 times logarithm of x. And the final term, we will just use the power rule, add 1 to the half, and divide by 3 over 2. Dividing by 3 over 2 is the same as multiplying by 2 over 3. And we add a c because this integral is indefinite. Next example, we are told that cos x over sine square is in the integral, and there is 2 multiplied by e to the power x. We can treat these two terms as 2 separate integrals. That's the same as having cos of x over sine of x, and another fraction sine of x here, and having another integral with minus 2 in front of it and e to the power x there. So we can treat this as two separate integrals and take them one at a time. So what is cos over sine? That's cotan. Over sine is cosec. Okay, if you've forgotten, have a look up in the top left corner. We know that's the derivative of cosec, but there is a minus sign that's missing. Okay, so we're going to put the minus sign in front of the original function when we get it. Okay, so we can say we multiply by this by -1, so that the final answer should be cosec of x. Coefficient of x is 1, so we don't need to worry about that k there. Okay, we know that the integral of e to the power x is e to the power of x itself, because that was the derivative of e to the power of x, and we will simply have this with a plus c, because this integral is indefinite. There are no numbers here to substitute, so we will add a plus c there. This example, we've been asked to integrate, we have actually the answer to the integral, and we have been asked to calculate the value of a. A is a constant that's given to us in the limits of the integral. So what we can do, as scary as it might look, we can divide this fraction into two parts, which are simpler to work with. So integral of 2x over x will simply be integral of 2, because the x and the x cancel away, and the integral of 1 over x is simply log x. So we're going to use that for our answer. So having integrated 2 with respect to x, we will get 2x, and let me get rid of my writing here, and log x. Now we can substitute the limits of integral 3a and subtract once we have the limits of a. Look, we're going to substitute 3a to be positive version of the upper limit, and we subtract the lower limit, which is 2a log a. At this moment, we can do some simplification. Multiply out the brackets. 6a minus 2 is 4a, and with logarithm rules, if you remember, we have subtraction of log a. That means 3a can be divided by a. We divide the inputs of the logarithms, and we end up with log of 3 there. So we will have one constant 4a plus log of 3. Now we've been told the answer to this integral is log of 12. So we work backwards from the answer to solve for a. So we equate this 4a plus log 3 to log of 12, and with logarithm rules you can subtract log 3 from both sides. That means dividing 12 by 3, which is 4. Now you have 4a equals to log of 4. At this stage, all you have to do is divide by 4, and value of a is a quarter of log 4. Now you can take a quarter here and put it to the power of 4, and a will equal to the square root of 2 actually. Okay, so using the logarithm rules, a can also be written as log of 4 to the power of a quarter. Now power of a quarter means the fourth root of 4, which means that we know square root of 4 is, and a square root of square root will mean log of 2. Okay, so that's this section of the course. The integrals in this exercise are mainly the reverse of the integrals that we learned, the derivatives that we learned about. So have a go at these questions and I'll see you in the next section.